Question number 6. We have a steel ball, we're given volume, we're given mass, we've got to figure out density. So we're thinking of an equation that links those. We know that the density is equal to mass divided by the volume. That's kind of the whole idea of density, isn't it? It's how much mass is in each unit of volume. Now, it's a 3-marker, so that might straight away make you think it's not going to be as simple as just putting the numbers in and solving. That's quite a straightforward equation. The difficulty comes from the fact that we've got the volume in centimetres cubed and the mass in grams, but we need to get the density in kilograms per cubic metre. So we need to turn these cubic centimetres into cubic metres, we need to turn these grams into kilograms in order for this to work. So what have we got? A volume of 3.6 cubic centimetres. Now, to figure out how many cubic metres that is, you've got to remember how many cubic centimetres there are in a cubic metre. And the key thing for this is that it is not 100. A lot of people get that one wrong. There's not 100 cubic centimetres in a cubic metre. And just to remind you, this is Y. Let's say that we draw ourselves, this is a cubic metre here. There we go. So let's make sure that it's got lengths of a metre, which of course is 100 centimetres. It's 100 centimetres tall, it's 100 centimetres wide, and it's 100 centimetres deep. So it's got a volume of 1 metre times 1 metre times 1 metre. It's a metre cubed. But in terms of the centimetres, it's 100 centimetres times 100 centimetres times 100 centimetres, which is 1,000,000 cubic metres, cubic centimetres. So there are 1,000,000 cubic centimetres in a cubic metre. Another way of remembering this is the factor for centimetres to metres is 100, but if we're doing it for cubes, then you've got to do 100 cubed, which is 1,000,000. 100 times 100 times 100. So we've got to take this number in centimetres cubed, we're going to turn it into metres cubed. We're going to need to times or divide. Well, there's going to be a lot more centimetres cubed in something than there is metres cubed, so we're going to need to divide by 1,000,000 on that one. So that is going to be 3.6 divided by 1,000,000. 0,000,000 cubic metres, whatever that turns out to be. Or, alternatively, you could have that as 3.6 times 10 to the power of minus 6. So, I'll just bring out a space there, let's get that in. So that's equal to 3.6 times 10 to the minus 6 cubic metres. The mass is going to be maybe slightly easier to convert. We've got 28 grams, mass is 28 grams. To turn that into kilograms, kilo means 1,000. Are we going to times or divide by 1,000? Well, there's more grams in something than there is kilograms. So this number's going to go down if we're turning it into kilograms. So it's going to be 28 times 10 to the minus 3 kilograms, or 28 divided by 1,000 kilograms. There we go. So those are your numbers, 28 over 1,000 and 3.6 times 10 to the minus 6. And if you put those numbers in, so let's move that up there. So our density is mass divided by volume. Remember, the mass is 28 times 10 to the minus 3. Your volume is 3.6 times 10 to the minus 6. Stick that in the calculator and that should give us our answer. Let's see. 28 times 10 to the minus 3 divided by 3.6 times 10 to the minus 6. That has given me 7777.7 recurring. So 7,777 kilograms. Let's see if we can just move this across here. There we are. Now it says here, do not penalise any significant figure errors. So if you had, for example, 7,800, that would be a good answer. In fact, to be honest, it would be better than 7777 because it would mean that you'd rounded the correct number of significant figures. So we're not penalising any significant figure errors in this question. You can round however you like. And if you've got the decimal place in the wrong place, then you get 2 marks out of 3. For that one, quite an involved one to start. It is a 3 marker though. Part 2, the steel ball is at a room temperature of 20 degrees Celsius. So we've got a second calculation question. It's going to have several different numbers in. Let's clear our board. There we are. Alright, so we've got, let's see, we've got the steel balls at room temperature 20 degrees Celsius. We know our temperature we start with. Let's then put in a pan of boiling water maintained at 100 degrees Celsius. So the ball is going to eventually reach that 100 degrees Celsius. So we've got a temperature going from 20 to 100. So straight away I'm thinking this will be a question with temperature changing, won't it? Theta for the temperature change, delta theta, is going to be equal to 80 degrees. We've got a change in 80 degrees Celsius there for our change in temperature. Remember that delta thing just means change, it's nothing special, and the theta just means temperature. Change in temperature of 80 degrees. We know the specific heat capacity of the steel is 510 joules per kilogram degrees Celsius. And we're trying to figure out how much thermal energy the ball gains. We're going to use delta Q for thermal energy. That was a pretty terrible Q. So we're trying to find out what delta Q is. We've got C and theta, and we also know M. Mass is 28 times 10 to the minus 3 kilograms. There we are. So we're trying to find delta Q. And the equation is delta Q is mc delta theta. So we don't have any rearranging to do that. Mc delta theta. It says use an equation from the list of equations at the end of the paper, so it's not one you had to memorise, and it will just be like that. So we're just going to multiply these three things together, the mass and the specific heat capacity and the change in temperatures, and that will give us our answer. Only a 2 marker, because you're just substituting in the values and evaluating. So show that on the mark scheme. A mark for substitution, we put the numbers in, and then a mark for the answer, 1100 joules. 1142 if you did it to 4 significant figures. There we go. So we're then told that the steel ball is put into a furnace, it's melting in the furnace, and we've got to describe them or compare the motion of particles in the steel when they're solid compared to when it's in the liquid state. So you're basically describing how the particles in a solid compared to the particles in a liquid. That's not that far off key stage 3 really. So for solid you can say the particles vibrate. There's a mark. They vibrate around fixed positions for your second mark. For the liquid state you can say that they're moving more freely there. You could also say that they are moving randomly. So remember we're comparing the two. For the full marks we need to be talking about the liquid and the solid and how they are similar or different if we are comparing. Good. And then the final part actually looks more involved than it actually is. They give you this big old table full of lots of information you won't have seen before. We're talking about solidifying molten steel. So we've got our crucible here, we're pouring our steel into our crucible. And we're told that the melting point of the steel is between 1425 degrees and 1540 degrees Celsius. We're going to work out how the steel worker gets his temperature time graph for steel as it goes from liquid to solid. So we're given 3 thermometers. Straight away we can get rid of one of those, because if we're looking at it as it goes from liquid to solid, we're going to be looking around the melting point of steel. So we're going to be looking around 1425 and 1540. And as you can see, the platinum resistant thermometer is going to be no good because it doesn't work with that range of temperatures whatsoever. So pick either of those thermometers and that will give you your first mark straight away. And then from there it's just describing what you would do to figure out the temperature time graph. So you've got to pour it in the crucible so it can cool down. You've already selected your thermometer, so that's your second mark. You can talk about starting the stopwatch, because of course if you're doing a temperature against time graph, you're going to need to know what the temperature is and what the time is. So we've mentioned that we're going to use the thermometer. We're also going to turn the stopwatch on when this happens, and then you let it cool down and you take the temperature at regular intervals. Now, unless you happen to have an intimate understanding of the volume of crucibles and the cooling rate of steel, it's going to be very difficult for you to select a time interval that's going to work. So they don't actually want you to do that. They just sort of say any time interval will be fine. You could do it every 10 minutes, you could do it every sort of hour or whatever. They're not expecting you to know how quickly molten steel is going to cool down. The example they give you is 10 minutes, but it doesn't really matter. So yeah, those are the things that you're looking for. Correct temperature, or correct thermometer rather, picked, molten steel poured into crucible, start the stopwatch, let it cool down, we write down the temperature every 10 minutes or so perhaps, or any even interval of time, and that will get you the marks. Any 4 of those will give you all 4 marks, and that is question 6.